So it's time to talk about radical substitution, and of course, whilst I will be covering the general stages to the mechanism for this very important reaction in A-level chemistry, I really want you to stick with this video right to the final chapter, which is all about problems and limitations of the mechanism. Lots of people forget about this, and it's a surprisingly big part of the exam questions. Like I said though, let's look at the specifics of the mechanism all through the stages here, using the example of propane and bromine reacting in UV light to form 2-bromopropane and hydrogen bromide. In this reaction, a carbon to hydrogen covalent bond is being substituted to become a carbon to halogen covalent bond. I've decided to make 2-bromopropane here as a product rather than just 1-bromopropane because it's going to give us a great opportunity to look at the specific ways to represent some structures and give some challenge to how we're going to carry out that termination. Our 3 stages for this radical substitution mechanism are, as they always will be, initiation, propagation, and termination, with initiation being our step 1. And at first glance, it seems very short, very sweet, but it does carry a lot of weight with some exam questions. In this stage, we see a molecule of our halogen undergoing homolytic fission using UV light. This means that the covalent bond between the 2 halogen atoms is breaking, and the 2 electrons from the bond are being shared equally between the 2 halogen atoms, the 2 bromines here in this example. This creates 2 halogen radicals. By definition, a radical is a species with a single unpaired electron. It's represented in the chemical formula as a single solid dot, like we can see here with the bromine in the products. Radicals are very reactive, and their formation leads us swiftly into stage 2, propagation. In propagation, we have 2 equations. Let's look at these one at a time. In the first one, we react our starter organic molecule from the overall reaction equation. So here we can see that's propane from our overall reaction equation just up here. And it's going to be reacting with the halogen radical we made in initiation. And we can see that bromine radical just there. The organic product of this reaction is incredibly important with its structure. Alongside our hydrogen bromide, we've also made an organic radical. Now look at that. Look carefully at where we have placed the radical dot position on carbon number 2 in our chain. Why have I placed it there? This positioning is important because it needs to match the eventual location of the bromine in the final 2-bromopropane product from the overall reaction equation. So you can see here I've placed the radical dot and lost the hydrogen from here in this middle carbon, because that's where I'm going to place the bromine long term in the overall reaction equation. You'll notice the 2 carbons at either end, just here, are completely saturated still with hydrogens. They are not going to see any substitution here. In the second stage, the organic radical now reacts straight away in the least well-remembered equation in this whole mechanism. In this reaction equation, the organic radical we've just made reacts with a fully intact halogen molecule, the same one from the overall reaction equation. That's the bromine, for example, here. In the products of this reaction, we can see that we have the target organic molecule, the 2-bromopropane, and we also have a halogen radical. Can you see how this halogen radical matches the one that was first used in propagation? Just up here. This means the halogen radical is regenerated by the whole process, and that makes it a catalyst in propagation. Finally now we have termination. In termination, the radicals we have used throughout propagation now have a chance to react with each other and make one molecule. They each have an unpaired electron. So quite literally what happens is those electrons get paired up. And so we end up with a regular covalent bond between the 2 radicals. This means we have 3 possible reaction equations using the different combinations of radicals that we use throughout the propagation process. Our first one here, actually really straightforward. It uses one of each type of radical that we had in propagation, and it makes the target organic molecule, that 2-bromopropane. Nice and straightforward. The second option, quite tricky. This seemingly makes a branched organic compound just here. So why is it branched? This is because the propane radical that we made and used in propagation had the radical dot positioned at the second carbon along in the propane chain. This means when two of this radical react together, they form a covalent bond specifically between those carbon atoms. So we don't just form a covalent bond at the end here and end up with one hexane chain. Instead, we have two molecules of this radical reacting together and they form a bond at their middle carbon points just here. And the product is 2,3-dimethyl butane. Draw it out to have a look. In the final termination equation here, this is the one that's least requested by the exam papers. We have two bromine radicals reacting to make one bromine molecule, and this is effectively the reverse of initiation, but it does nicely finish off the termination stage of this process. Now that we have the main stages out of the way, let's discuss the problems with this mechanism. There are two main issues. The first issue is that whilst I did write the overall reaction equation that you can see up here to produce the 2-bromopropane product, there is every chance that the substitution could have taken place at a different carbon atom, making 1-bromopropane, for example, and sadly, we are unable to control this. The second issue is that further substitution of another CH bond could occur and form something along the lines of maybe 1,2-dibromopropane, so that's more than one CH bond being used, and again, sadly, we're unable to control this. The second issue is that further substitution of another CH bond could occur and form something along the lines of 1,2-dibromopropane. So that's more than one CH bond being used in the substitution. Again, sadly, we are unable to prevent this. In fact, it's even got a chance of having all of its CH bonds entirely replaced by bromines. That would be complete chaos, but it could happen. Thank you very much for watching this tutorial. Maybe it's time you took a look at the curly arrow organic mechanisms. Click the link on screen now to go to a full summary of those that you need for the OCR A-level in chemistry. Or maybe you want to start looking at the exam papers. There's some unified chemistry papers in this playlist that are linked on screen now. Either way, and until next time, happy revising.